I'm trying to run around this morning, upload a paper and changes. I'll get it for you. All right, so we have gone through all the things dealing with tuning, really either with either with capacitors and inductors in series or parallel, or using either shorted or open stub tuners, right? So we've covered the whole gamut of how you can tune something using it's connected to a transmission line so you get no reflections. Now the next thing we're going to do is something called a bounce diagram, and this is shown in at the end of chapter 2. Where it is, if you have your books. This is important in this day and age, so you know how to do this. So, if you look on page, it's called transient analysis. And this starts on page 87. Can you all see that, class? If you have your books, take a look. So I'm going to go through this. I'm going to try to make it real easy. Think of it this way. If you had a rope and you secured it to the wall over there, you follow me on this? So you secured it to the wall. And you did this. You would create a wave that would propagate, hit that wall, and then bounce back. It would hit me, keep bouncing. You all follow me? That's the same deal with what we're dealing with today, and it has to do with really a transmission line with a load. So this is what it looks like. You have a transmission line. It has some characteristic impedance Z0, then it has a load, ZL. Now our loads are going to be strict real for this part, and so is Z0. So it's going to have some value, call it R load if you want, it could be Z load. It won't matter at this point. This transmission line has a certain length, L, right? And then we're going to have something that's going to be a switch. It's going to really close at T0, T equals 0. Now you're familiar with switches from your circuits course, right? When you did transient, you had a switch, it closed, and the whole thing started at the point the switch closes. It'll always be at T equals 0 for me. And then over here, I'm going to put a resistor here, RS. This is important if you follow me on this one. This is not something you've seen before. And I'm going to have a battery here. And it's just going to be some, I'll call it V0. All right? Now, y'all follow me on this. You got a battery, some voltage. This switch closes at T equals 0. What do you think happens? A wave starts propagating down at the speed of light. If it is the speed of light. Y'all follow me? And when it hits that, it's going to reflect back, come back and hit here, and then reflect again, reflect again. I'm going to at least understand the concepts, right? Not hard to understand. So we're going to assume right now the velocity on this line is going to be, the phase velocity is going to be the speed of light. But it doesn't have to be. It could be the speed of light divided by the square root of the epsilon relative of that transmission line. Y'all follow me on that? So it doesn't have to be the speed of light, but we're going to assume it is for this purpose. Make life easy. So now the next thing we do is calculate the time it takes. And this is time it takes to go, I guess, a length L. So that's going to be simple. They just call this, I forgot if it calls it piece of L or what. It doesn't matter. I teach this in several different books. He calls it TL. Yeah, piece of L. So piece of L is just the time it takes for the wave to start propagating and finally hit there, go down one length. Y'all follow? It's just the time it takes to go down one length. So that's just going to be the length of the line divided by the velocity, and I'll call it the phase velocity here, even though we're going to assume C. That's the first thing that's important. Now the next thing we need is we need the reflection coefficient. Please follow me on this one. People will mess this up. Not this part, but the next part. Right here, we have a reflection coefficient of the load. Do y'all follow me? The wave comes in, it hits. Some is reflected, some is going to be dissipated or transmitted. Do y'all follow me? So that reflection coefficient, just like before, is always the impedance you're going into minus the impedance you came from, which is the characteristic impedance of the line, divided by the sum. Everybody okay with that? Straightforward, right? It will be a strict real number if the load is real, and it will be real for this part. You all with me? Now, over here, when it hits, it's reflecting back, and I'll get to that, but it hits here. Now, do y'all remember when you did Thevenin equivalent circuits? Remember how if you had an active source, a DC source, if you wanted the Thevenin equivalent resistance looking into that area of the circuit, you shorted the battery. Do y'all remember that? Here you short this battery too. And if you look this way, the actual resistance you see is RS. Do y'all follow me? So now you have a reflection coefficient here. And that's at the source. And that's going to be the impedance you're going into. Remember, it's coming from there going this way. So it's going to be RS minus Z naught over RS plus Z naught. Y'all with me so far? So what happens? Switch closes, a certain amount of voltage, by no means all the voltage, but some of it gets on here, goes down, the speed of light hits here, then some of it is reflected, less than actually hit there, hits here, and it keeps going back and forth, and asymptotically it goes to a steady state value. You all hear me on that? Now, the way we do this is kind of interesting. We first say, just as that switch closes at t equals 0, what we do is find the voltage right here that's going to be, and I'm calling that V prime, that's going to be actually introduced to this line and will propagate the speed of light. Remember, this line, when that switch closes, doesn't know what's down here. The only thing it knows is the impedance it sees right here. Y'all follow me? Everybody on this one? All right, so at t equals 0, that V prime, that's going to be the actual magnitude of the wave that's going to go down there, will be Vs, and then it's just going to be Z naught over Z naught plus RS. So if there was no RS, effectively it would just be Vs. Do y'all follow me? There's no source resistance. How many understand this right? I don't mean to go so fast. I'm trying to just get the basics out of the way that you can see easily. Okay. Now for the bounce diagram. Pay attention to this. We do something where we actually do this. We take a look at time on this axis, and then this is the length of the line, and here's where the load is, and here is the source. And we do this. We start out, we say, as time progresses, we're going to have a wave front that's going to have a value V prime moving this way. You're just going to have to bear with me on this. I'll get to what all this means in a second. It hits, and there's going to be, and it's going to, the time it takes is going to be TL. It'll take the time it takes to get to the end. Y'all follow me? You'll see this in a second, the way it works. There's so many things I have to bring into the picture at one time. I'm going to just draw it and you'll understand. Now it hits here, and it's going to hit at the time associated with TL right here, and call that this. Then it sums reflected back, right? And it hits here, and this would be another TL. This is not drawn to scale. And then it would keep going. Do y'all follow me on this? So this one would be gamma L, reflection coefficient, times V prime. This one would be gamma L times gamma source times V prime. Everybody follow me on this? Give me a show of hands if you understand what I'm doing. All right. Now, here's how you actually figure out what the voltage is anywhere on the line. This is the important part, and it is in your book. Can you give me the page number which shows that bounce?
88.
88, page 88. Y'all hear me? So, here's how you do it. Suppose I want the voltage versus time right down the center of this thing. So I wanted it L over 2. Y'all follow me? So I'm just going to do this. So if this is L over 2, right here, this point, I draw a line straight down the center. Y'all follow me? Now, next, I get? And this is time, and this is the voltage that I'm going to actually measure, get at the middle of the line. V at, really it's at L over 2, comma T. This is 0. Now I know at TL, the wave has gone all the way down, 2TL here, and I'm going to keep going. So we know the voltage at the center is going to be 0 until the wave gets there, right? You all see it would be TL over 2 because it's halfway down? How many see that? All right? So at TL over 2, whatever that is, it's going to jump up and it's going to be V prime here. You all with me? It'll stay V prime if there's no bounce. But there is a bounce. Now it goes down. Now just think about this. We started here, it's 0 volts from here to here. You all see me? I'm doing one of these things. That's T. This is the length of the line. The only time you're going to get a change in voltage if you come down from here at 0 is when you cross that bounce path. You all follow me? Then it goes to V prime. You all follow me on this? Can you see it over there? Everybody? Now it's going to stay there until what? Well, that's TL, and this is going to be another, that's 3 halves TL, right? And what's going to happen? You're going to add this to it. So when it hits, and I'll try to show you this, when this is TL over times 3, or 3 halves, pardon me, 3 halves TL right here. Now it hits, and it depends what the load is, it could go up or down, but now the new value is going to be V prime plus V prime times gamma L, or you could write it as V prime times 1 plus gamma L. You all follow me? How many see this? The idea. All right, now it's going to stay there for how long? Well, another full TL, right? And then what happens? Then I add this onto it. You all with me? Then I'm going to add that on. I keep going, so down here to 5 halves, down here somewhere, and this is where it gets messy. So this would be 5 halves TL. And now it's going to jump up. And it's going to be either go up or down, I don't know, I'm going to have it go down, but it's going to be, now it's going to be V prime plus V prime gamma L plus V prime gamma L gamma S. Do you all follow me? How many see this? And you just keep on letting it progress. Now there's one thing that's very interesting that I'm going to share with you. And we'll do several of these things so you get a good feel for it. It isn't hard. Just keep in your mind to always get the right value of the reflection coefficient to load, reflection coefficient to source, the time it takes to get down there, and then accurately draw this bounce diagram, all right? So here's the one thing. As time goes to infinity, you with me on this? As time goes to infinity, then the transmission line appears as just 2 pieces of metal, 2 conductors that are tied right to ZL, and you have RS. Do you all follow me? It becomes a simple DC circuit. As time goes to infinity, your circuit looks like this. You're going to have the same value of V0 here, and you're going to have RS. And now you just remove that transmission line, and here's going to be RL or ZL. So the voltage that will be on the transmission line is the voltage across this load. Now these 2 pieces, this transmission line looks like a couple of short pieces of metal. Think of it that way. So what's this voltage going to go to? Asymptotically, it's going to go to simply, and I'll call this V load, is equal to V0 times ZL over ZL plus RS. That's how you know you're on the right track. When you take a look at the bounce, it's going to asymptotically jump up and down and then settle at this value, anywhere on the transmission. You with me on that? Okay. So with that in mind, one last thing I'm going to tell you. It does get a little confusing. And I'm going to erase this. Sure. These are not hard to do. Oh, yes. If you have engineering paper, you know, the green with the crosshatches or something like that, or graphic, it's much easier to do this because you can accurately draw these things with the crosshatches and stuff. Just remember that. next, I'm going to draw this, and I got one thing to mention. So, just drawing this. As such, this is important. Here's where the load is. Right here. Now, if you were to take a look at the voltage at the load, I'm just going to leave it as V prime. You know where that came from, right? That came from the beginning when we did voltage division to see how much voltage gets on the transmission line to propagate. You all with me on this? This is important. Just listen. You don't need to write it. If you actually look at the voltage at the load, and I'll call it Z equals load value right here versus time right here. All right, well, we know it would be 0 until I hit TL, right? Because it'll take that long to get down there. But when it hits, this is very important to see. If you were right here and looked at it, you'd see that the voltage V prime is there and also V prime gamma L shortly after, right? But as you get closer and closer to this point, these two superimpose, both the incoming and outgoing. Do you all follow me on that? The voltage here will be V prime plus V prime gamma L. All right. So when it changes, it goes to a value here of V prime plus V prime gamma L, or V prime times 1 plus gamma L. And 1 plus gamma L is often called tau, or the transmission coefficient. How many remember seeing something like that somewhere else? Anybody? Transmission coefficient is used all the time in engineering, as well as reflection coefficient. In your laboratory work, were you talking about reflection and transmission coefficients or not? I'm not sure really. Physics labs, maybe. Engineering labs, until you get into transmission lines and stuff like that, you probably don't deal with it. I think I have one physicist doing it, don't I? Or not?
He's not here today.
Oh, well, and he skipped. Typical physics. All right, so that's the value. You all follow me? Now, it's going to stay there for what? Takes one more time constant to get down here, or T sub L, one more. So for 2 TLs, you all follow me? And then it's going to change again. It's going to stay there, call that 2 TL, and then 3 TL. And now what's going to happen? Now it's important you see this. Okay. So you had this value, right? Now what are you going to add to it? It comes down. Hits, this one's coming this way, this one's coming this way. You all follow me? So now when you superimpose them at that point, you're going to add this and this to what was before. So now it's going to change, and I don't know if it's going up or down. I'm going to have it go up. And now what's here is going to be that, which is going to be V prime times 1 plus gamma L, right? But it's also going to be this and this added to it. So it's going to be plus gamma L, gamma S, plus gamma L squared times gamma S. Y'all follow me? Now remember, you have to add, superimpose the incoming and outgoing when you're at the low. And same here, when you're right here, remember, there's going to be an incoming and an outgoing wave when you're right here too. And you have to superimpose, you have to add them both at the same time. Y'all with me on this class? Let's do a problem, see if we can get it right. Mistakes on this one are usually because you're bored. It's so easy. You'll make mistakes, you'll misread the load, you'll do something. So you have to focus, have to force yourself to be attentive on this. And I'm not the best at this, especially if I'm in a hurry. But if I'm going to get paid for it, I can be very attentive. So let's do example 2.9, all right? Is this all right with everybody? I want to do this example. All right, erase this. By the way, is our next basketball game here? I didn't know.
Yeah. Is it Mizzou?
Huh?
I know
You guys
Mizzou's
go to
Tuesday.
games or-
We're going to Alabama this week.
There it is.
Yeah, but is it, don't we have a game before then or not? I thought we did.
It's Texas A&M.
Is Alabama 1 or 2 now?
They're 3 right now.
They're 3?
But Purdue just lost, so we'll see.
All right, well, never was a basketball fan until Bruce Pearl got here. Then I got to be interested, especially when I started walking around and seeing this guy Kessler's. That tall and some of the others. Anyway, let's do that problem. Can you, anybody, what do we got here going on?
An example will show how the step change in voltage propagates along a section of T-line, how the bounce diagram works. We want to plot the voltage at the middle of 6 centimeter long T-line.
All right, hold it. Let me get this drawn up. What's the battery?
4 volts,
And what's, oh, we got RS here. What's RS?
25 ohms,
RS is 25. What's Z naught?
75 ohms,
What's this right here?
125.
So Z equals 125. And what's the propagation velocity?
0.1 C.
0.1. That's a lousy transition. So it's only a tenth of C. Go ahead. Then the length of the line?
The voltage at the middle of a 6 centimeter long T-line.
6 centimeter. So it's 6 centimeters long. They want it right here. This is an easy one. We just did this one without the values. You with me, class? So let's go through this together. Make sure you follow. There's no real order you have to do this in, because they're not based. One calculation doesn't in any way, shape, or form impact the other. First, I'm going to get the reflection coefficient of the load. And what is it? It's always the impedance you're going into, 125, right? Over the impedance you came from, over the sum of the two, which is 200, right? So that's going to be what? Minus 1/4, isn't it, class? I'm sorry, positive 1. My bad, positive. It's my habit of getting hurt. You all with me on this, class? Sorry. Positive 1/4. Next one I'm going to get is here. Reflection coefficient of the source. So that's going to be 25 minus 75 over 100, or 25 plus 75. And that's going to be minus 3/4, right? You all agree with that?
Minus
Sorry.
1/2.
Pardon me?
Minus 1/2.
Minus 1/2. My bad. Minus 1/2. Then I'm going to find the time it takes to go down the line. So that's going to be the length of the line, which is 6 centimeters. 6 times 10 to the minus 2 over the speed, which is 0.1 times c, or it's going to be 3 times 10 to the 7th, right? So that's going to be 2 times 10, and that's going to be, looks like minus 9, right? Or 2, and that's going to be nanoseconds, correct, class? You all with me on this? So we got that. Now we need to get V prime right here. And what's V prime going to be? That's just going to be the magnitude of the wave that will start the propagation. Remember how to do it? What do we start with? The voltage here, right? So it's got to be 4. Now what's it times? Simple voltage division. The impedance here, right, which is Z naught, put it down, over Z naught plus RS. So that's 4 times 75 over 75 plus 25, and that's going to be 100. So that's really 3/4 times 4, or 3 volts. Is that right? I got one. Playing Jeopardy. All right. Now I'm going to go ahead and draw the bounce diagram over here. And these always have the same shape. Values will change on here, but the same shape. I don't know how far they want to go. So here's 0 time-wise, and this is the length, L here. And if you look at this, so this right here would be TL, and I'm just going to leave it as TL. This is going to be 2TL. This is going to be 3TL. This is going to be 4TL. And this is going to be 5TL. And 6TL. All right. So they want the value of the voltage dead center, right? Right here. And we're going to go ahead and get it. And I tell you what, just for kicks, I'm going to put this. This is 3 volts hopped on here, right? That's 3 volts, and it's propagating that way. That's V prime. Y'all follow me, class? All right, now, it hits here. What's coming back is going to be 3 volts times 1/4, right? Or 3/4 of a volt. Do y'all follow me? Everybody? So this is 3/4 of a volt. Now when it hits here, that's -1/2. So I have to take -1/2 times 3/4, which is going to be -3/8. Do y'all follow me? This is -3/8. I'm not sure what he has in his book on this. This comes down and hits this, so it's going to be -3/8 times times 1/4, right? So now it's getting to a small value. -3/8 times 1/4 minus 3/30 seconds. And now it's going to get smaller and smaller and smaller. But y'all follow me on this? It's asymptotically approaching 0 as it bangs around here. It changes. So now we graph it, and he wants it at the center. So here's T. And this should be, since it's nice because the time it takes to go down, there's 2 nanoseconds. So I'll just call this 1 nanosecond, 2 nanoseconds, 3 nanoseconds, 4 nanoseconds, 5 nanoseconds, 6 nanoseconds. Let's take it out to there, and this is going to be the voltage at the center. And this is at center of transmission line. Y'all realize it takes 2 nanoseconds to go all the way down. It would take 1 nanosecond to get halfway down. Y'all with me? So no voltage at all until it hits 1 nanosecond. Then it's going to go up to, y'all see it? 3 volts, right? Right? And it's going to stay there for how long? Well, here and then here. So a full 2 nanoseconds, right? It's going to, right? Because this is basically halfway down, halfway down. It's a full time constant of 2 nanoseconds. So at 3 nanoseconds, it came here, hit. So at 3 nanoseconds here, I have to add 3/4 of a volt. So it's going to jump up. Does he have this graph, by the way?
Yeah.
Does he have this as 3.75?
Yep.
Or not?
He does.
He does. It's going to stay there for how long?
2 nanoseconds.
It's going to keep going. That's exactly right. So here, that's 4. Here's 5 right here. At 5, what's going to happen? Well, let's see. Hits here. Now I subtract -3/8 from it, right? So what is that going to be? That's 6/8 minus 3/8 is going to be plus 3/8. So it's going to come down a little. And this is going to be 3 3/8 volt, whatever that is. But you all see how the progression works, right? What else does he ask? On that one. Anything? Is that it?
That's it.
All right. For kicks, let's do the voltage at the, yes, sir.
I'm just wondering, like, okay, so you send out the wave, and it's waving.
No, it's not waving. It's It's not wavy. This is a transient pulse, right? It's not oscillating. What is it? It goes from, think about this, if you have a string tight, right? And you just jack it up and hold it. It stays that way and this transitional period propagates, right?
Okay.
Y'all
So
follow me on
we're
this
not
stuff?
dealing with an AC wave.
It's a transient with a DC source, right? Remember with DC sources, they asymptotically approach one value to the other, right? All right, this is a DC source. I wish I had in physics, actually when I was in school, they used to do this all the time. If you tie a rope there, this is a mechanical analog of it. You go like this, because that would be like increasing the voltage on the end. You'll see the entire rope just move up from this level to this level and stay there until it hits. Then it'll reflect back. Does that make sense to you?
Yeah, I thought it was just AC.
It's nothing's doing this. You need an AC generator for that. This is not an AC generator. It's a battery with a switch. So it goes from, it's basically, you know what happens when that wave's moving down? It's charging up the capacitor. It's effectively that transmission line. That's exactly what's going on. That's it. And but these kind of problems are important because when you guys do any kind of real work in the world where you're doing Cat 5 or transmission line work, and you have to figure out where a short is in an open. They send a pulse down, and on an oscilloscope they look at the time of the reflected signal, and they know there's something out there that it hit and reflected back at, and it actually went twice the distance. So they'll know the velocity of the wave on that either Cat 5 or transmission line. And what they'll do is they know C times that time is actually 2R, 2 times the distance that it went. So that it takes C, or the velocity on that, times the time it takes to, from the time you sent the pulse to its reflected, and they'll divide that by 2, and they'll figure out how far down the line it is. So if they have to dig through a wall or something, they'll figure a pretty good idea where it is. And this is real, because I've had to do kind of stuff like that drives me nuts. When you run anything behind a wall or underground or anything like that, it's not easy to get at this stuff when you bury it, or especially behind walls. So you have to know about exactly where that thing is probably the fault is, so you can go in and open it up and repair it. Now, I don't know what they do now with fiber optic cable, but it's typically that kind of thing, because fiber optic cable is buried under the earth, and the biggest problem with fiber, it used to be, I don't know about now, it used to be that rodents, in any buried cable, rodents like things made from oil, like the insulation. Does anybody else have problems like that? Do you know about it? Just as an aside, I own a bass boat, and I had parked out at my friend's house when I was getting a new house moving, and I came out there to get it, and all the wiring was chewed up by some mice and rats. I mean, everything. I didn't know that these guys love the oil. They think it's food, and they eat up everything. Well, when they bury stuff underground, they're going to find it eventually, and they will chew through it if they can. Nowadays, they probably have some protective coating or some kind of bitter taste or something put on there, but that used to be a real problem. Has anybody heard of this before?
Yeah, my uncle's Mustang, it just, like, it was like corn on the cob, just like teeth marks all down.
That's a good way to put it. So, but you know, when they bury these cables, they weren't thinking that way at first. They didn't. I mean, the people that are engineers aren't generally pest control people. They don't know that these guys do that. And so they had a lot of problems early on that they probably solved. Okay. I want to do the value of the voltage at the load just to make sure you see this for this same problem. So guys, you work with me, show me. I'm just going to go, so this is 2 nanoseconds, right? 4 nanoseconds, 6 nanoseconds, 8 nanoseconds, and 10 nanoseconds. Okay? Now you tell me this is going to be voltage at the load. What happens? We start here, we've got 3 volts, right? It's coming down. It hits. There's 3 volts, but at the same time it hits, you got to add 3/4 on. Y'all follow me? So it would come down here, 2 nanoseconds, and would immediately go up to 3.75 volts. Everybody follow me on this? It'll seem simple until you start doing these things and they ask something that's not quite the same. All right? Nothing happens. here, right? That's going to be what, 4, right? Keep going. At 6, what happens? Now take a look at that. I have to add this and this, right? Y'all follow me? To the prior value. How many see this right here? Because it's superimposed at that point, right? So I don't know what that is. Minus 3/8 and minus 3/2 or 30 seconds. Add that to this value. So what is that? It's going to be down from it, right? But what is it?
It's almost like a half.
12 and 3, 15, 30 seconds, subtracted from 3/4. I don't, what is
We got 3.28.
3.28, anybody? Is that one of the values he has in his, at about,
Yeah, that's
Yeah.
correct.
so what's the value again?
3.281.
3.28?
1.
281? 281 volts. Y'all follow me? It's going to keep doing that for another 4 seconds, right? Stays there. And then you got to add the next group. Do y'all follow me? How many see this? It seems boringly simple, I know, but people mess this up. Now, here's the question. If I asked you for the current that would be at this load right here, how would you get it? If I asked you for I load versus time, just talk to me. It's as obvious as it seems. Do you know the voltage at the load? It's right there, right? How do you get the current? Divide by the load. Do you all follow me? That's it. That's all you do. Now, if you ask for the current at this end, this gets a little interesting. All right, hear me now. Very carefully listen. You need the voltage here at the sending end. And remember, that's a superposition of these things at the time, right? Then you have to take that voltage. Now, hear me. Take that voltage, don't divide by Z0, don't do anything like that. Here's what you do. You take the VS, the 4 volts, and you subtract that voltage from it, and then you divide by RS, because that's the voltage across that resistance. You all hear me? That will be the current that's going to be moving onto the transmission line. Don't use Z0. It's not Z0 any longer. Okay? So if you wanted the current, like if I asked you for the current here, I at the load versus time, you first need the voltage at the load. So you've got to do the bounce diagram to see what the voltage is. Then to get the current, you take 4 minus that voltage. So you find the voltage across this resistor and divide it by 25. Y'all hear me on that? Yes, sir.
Is this the current at the source of the load?
Huh?
Is this the current at the source of the load?
At what?
The current, where are we finding
We're at this is called the source, right? It's where the switch is. You can call it whatever you want. The load is always at the end.
All right.
Right. So we're asking for the current that would be flowing onto the transmission line. So you find the voltage here, subtract it from 4, that's the voltage difference across the resistance divided by the resistance. How many understand that? It's important you don't mess that up, because here's what I'll say. And I do this, I say this all the time. And even students that are graduates, they'll take this voltage here and just divide it by Z0. They get careless, that's wrong. It's the voltage here minus the voltage here divided by RS, so you can figure out the actual voltage difference. Okay? Yes, sir.
So if you're taking the current at the load, I guess,
This is
are you dividing by Z0 or Z0?
this is no, it's by ZL. Right here,
Okay.
there is no other voltage, right? There is no other place. This can't flow past this. So if you have the voltage there, you divide by ZL, you have the current.
And if you're in the middle of the line, you divide by Z0?
Well, at the middle of the line, if you want to, first I'm not going to ask you that.
All right, okay.
All right, at the middle of the line, the current is going to be the same thing as the current here when it's transgressed. I mean, you have to give the time delay to it. But I wouldn't worry about that. It's really, they want current here or there. They want voltage throughout the line. Okay, good. Now, one last thing. Because I got through this and I'm very happy. Whitmore's book does some stuff where he has loads that are not going to be just strictly resistant. He has inductors and capacitors. Don't worry about that. I'm not going to test it. That's something for later on. It'll come later in your career. You're going to get this kind of stuff. You can solve it, but it's with differential equations. I'm trying to keep away from too much attention to stuff that you're not really going to need right now. And now we're going to start chapter 3. I'll give you homework on this stuff. So you all had physics, you had basic electrostatics, and you had propagating waves in a very basic way. So we're going to go back and revisit this, but it's going to be applied. And I want to say one other thing. Everything that we do in electromagnetics is not based on pure math, even though it looks that way. It's based on measurements, and we find equations and formulas and physical reasons why you can write these laws so precisely mathematically. But it's not like Moses came down from a mountain and said, you know, here's the way it's going to be. These are all based on measurements, and there's some very famous, really physicists, engineers, scientists, whatever you want to call them, that did these measurements. And one of them was Ampere. How many have heard of Ampere? All right, Ampere was the guy with the current law, right? The first started DC laws. Another guy was Michael Faraday. Have you heard of Michael Faraday? Faraday's famous for transformer action, right? Two physicists did a lot of measurements. And basically, I'm just going to give you the 5-minute version of the history of this stuff. It omits a ton of it, but the basics. So, a guy named Ampere, and don't write this down, just listen. Found that curl of H, and this is an abbreviate, this is a differential form, his was an integral form, is actually equal to the current. And I'm going to put DC on it. Now don't write this down, just listen. How many have heard of Ampere's law and recognize something about that? Looks like an Amperian law, right? Then Michael Faraday came along and he found the curl of E was actually equal to minus mu times dH dt. Now, that's actually minus dB dt, but I'm writing it in a more common form. And if you look at that, when you start working the stuff, and you look at the time-varying H field, there's another term that appears right here. And that's where James Clerk Maxwell comes in. And he figured it all out. And he found out that right here there's something called the displacement current. This is called conduction current density. This is displacement current density. And I'll get to all this in time. That's time there. And then James Clerk Maxwell came up and solved. He got one equation with one unknown in E or H, and he solved it and found out what the velocity of light should be. And in fact, it was. This predates Einstein. It predates Michelson-Morley and all that stuff. He had it mathematically. He knew what it would be, even though he couldn't measure it at that time, based on these equations. Now, a lot of this is going over your head, but just realize that's how things happen in the real world. They are based on measurement. And then we get mathematical equations that express it. So the first thing we're going to talk about is charge, that you're all familiar with. So if we have a point charge Q, it's occupying no real space or volume. It's just at a point. And we're at a distance r away from that. We get, and we have another charge. Here's the way they do it. I'll call this Q1 and this Q2. That's a distance r away. There's going to be a force on Q2 caused by Q1. Now, you all remember that, right? Back in the day, it was a squared law. So what is this force on Q2? The force on Q2 caused by Q1 is going to be Q1 times Q2, right? Then it's going to be divided by, normally they put a K here to explain this, it's divided by 4 pi epsilon naught if it's in free space, and it's divided by the distance squared. Now that's going to be just the magnitude, and then it's times a unit vector in the direction that goes from Q1 to Q2. So there's something called a unit vector, and I'll just call it I'm not sure what he calls this in the book. I'll call it AP. Doesn't matter. All right, so that's going to be the force. Then it will be in newtons, right? It's not in slugs. That would be the English system. You're used to seeing when you go buy something, it's in pounds, right? Pounds. It's a force, but I mean, this is would be slugs. Actually, it'd be in pounds, but this is newtons. It's different. Now, if you look at this, what is this a sub p that I put here? Well, a sub p is really the vector distance r over the magnitude of r. Here I need to talk about this. So when I talk about a vector distance versus a scalar magnitude, what do I mean specifically? If you're in Cartesian coordinates, you're used to seeing a vector r drawn as some I'll call it this, x and it's ax, where ax is a unit vector, plus y times ay, plus z times az. Do you all follow me on that? X, y, and z can be anything. But that would be a vector. Y'all, it has magnitude and direction, correct? If I look for a unit vector, it would be just r vector divided by magnitude of r vector. So how do I get, it would be this, x, ax plus y, ay, plus z, az. And how do you get the magnitude of the vector? Remember the orthogonal components. How do you always do that? You square the coefficients, right? The orthogonal coefficients, and take the square root. So this magnitude would just be equal to the square root of x squared plus y squared plus z squared. Remember, a unit vector has to have a length of 1, a magnitude of 1. That's what unit vector means. Now, that's what would go right here, where I have AP right here. And I'm going to put it in here. It would be r vector over magnitude of r. Now, if you take a look at that, something should ring true. You see how you have r squared, that's strict magnitude times this? This is really r cubed, isn't it, class? You all see that? So I'm going to just make this r cubed right here. And that is the force between two charges. If either of these charges is negative, if you have a positive and negative, then the force is actually in this direction. It's called attractive. They're attractive. Negative and positive attract. Two positives repel, two negatives repel. And that's basic physics. Y'all agree with that? Okay, so that's basic forces. And Dr. Whitworth talks about this, and he talks about vectors and how to get vector dimensions. I think you've had all this in mathematics and physics, right? You know about vectors, I assume. All right. So next, after that, we have to talk about differential surfaces and differential volumes. Now, a lot of this, I'm doing this lecture based on the fact I think a lot of you have seen all this in fair detail in physics. I'll get to the problems and we'll flesh out any other things that we need. But now I need to talk about some of the differential volumes and surfaces that we encounter. And we're going to spend some time on the different coordinate systems too. So next, the fun thing. All right, so that was a simple thing, differential vector in Cartesian coordinates, right? X, Y, and Z. If you have, how many have heard of cylindrical coordinates or polar coordinates? Y'all are with me on that? So here's how they work. If you had, in general, if we have X and Y here, and we look, and we're at a point that is given by X and Y, it also can be given by a radial vector distance, which is given as rho, and an angle measured from the x-axis that we'll call theta. Y'all with me on this? How many remember something like this? All right, so rho itself would be equal to the square root of x squared plus y squared. That's strict magnitude, always positive. And the angle, theta, would be what? Well, if you look at this, the height of this is y, this distance is x. Therefore, this angle would be, the tangent of this angle would be y over x, right? Or this angle would be tan minus 1 of y over x, an inverse tan. Y'all agree with that? So that would define either the polar coordinate rho and theta, or the Cartesian coordinate x and y uniquely define that point in a 2D frame. Y'all with me? There's also the z-axis that's coming out of the board, and that will be invariant with either either cylindrical or Cartesian coordinates. Y'all with me? Z stays the same. Now, when you talk about this, if you talk about a differential volume, I'm going to try to get this up. And here I'm going to put Cartesian, I'll just put x, y, z. And here I'm going to put cylindrical or polar. So when I look at this, polar coordinates are going to be rho and theta. And I look at or differential volume, really. Differential volume in Cartesian coordinates is just dx, dy, dz. It's a scalar. How many remember that? In polar, what is it? Anybody? Well, it's what? R, right? Times d theta times d, or not R, but rho d theta d rho. And I'll explain why. If I look at this right here, look at the tip of this if it wiggles, right? Suppose it wiggles a little. This would be through an actual angle d theta. Well, this length here, the dl length of this tip, would be equal to rho d theta. In other words, the wiper tip, like on your windshield wiper, if the actual angle you move is d theta, very small angle, the tip itself will move proportional to the length of the wiper times d theta. That's the length there. So if you look at this, the differential volume, or differential, I should say, this is surface, I have to put dz on that, would be this distance times this distance. So it's d rho times rho d phi, and it should be dz for volume. All right. I am out of time, I realize it. I'm going to pick that up next time. I'll give you some problems on bounce diagram, all right, and we'll go through them. Thank you. If you want your quizzes, I'm going to go upstairs. How many want their quizzes? I'll just give them to you, just follow me up. I'll go to 423. Thank you.